Welcome to this video on interference. This is part 1 where we're going to explore another wave phenomenon that occurs very closely with diffraction. And this is oftentimes referred to as double slit interference and is attributed to Thomas Young, who first described the process in the best detail to that point in the early 1800s. So let's jump in here and take a look. One of the famous experiments is seen here from above. Now we have to keep in mind that lasers were not invented at the time, and so Thomas Young did not use a laser but used some other light source, the sun or something like that, put a filter in between so that he could filter out all other wavelengths except for the wavelength he desired. Now here I'm using a laser because I know that I can get a specific value of a specific wavelength, and that is what we refer to as monochromatic light. Now you'll see soon enough why it's important that this experiment is done with monochromatic light. So I have a 520 nanometer laser here, and it is emitting this light that's hitting these two slits here. Instead of just one slit as before that we saw with diffraction, we're now hitting two slits. And you would expect to see maybe a coning out of each slit that we saw before in the diffraction patterns. But here, in fact, what we're seeing is represented here on the screen. Now, the light's not actually coming out of the wall here or the screen here. I'm just doing that to show the relative intensities. But you can see here on this front head-on view that there's this bright central maximum, and this is the term that is used to describe that middle piece of light, so the central maximum, and then there's a dark spot on either side of that, then another light spot, a dark spot, and so on. Now if we were to switch the laser to red light, we would see this pattern. Now the red light that I've selected is about 700 nanometers, and then the violet light, which is a shorter wavelength of 400 nanometers, we can see here. Hopefully you can notice that the red light has a more spread out pattern, interference pattern, than the green light, and the green light has a more spread out interference pattern than the violet light. Now this leads us to believe, or to reason, that the wavelength of the light that is incident upon the slits has an effect on the interference pattern. So we have to keep in mind here that wavelength is going to be a variable that seems to affect the shape of the interference pattern. Now what we're going to see here in the next video is how to mathematically set up this process so that we can represent mathematically how these patterns show up. But let's first take a conceptual look at what seems to be happening. Well, the first thing that we need to think about here is diffraction. So we have this idea of diffraction set up, and that is that the wave can bend around an opening or bend through an opening or around an obstacle. And the process by which we described that was the Huygens principle that wave fronts are made up of wavelets, and when it hits a boundary that is close in size to the wavelength of the light, that we should see just one wavelet or so coming in through the opening and creating that redirection of the light. Now, instead of just having one opening, of course, we have two. And so what we see is something that looks like this, where we have two little openings, and now we're going to have two different options for the light to diffract through. So let's say that one wavelength or one wavelet hits each opening, and we start to get the wavelet making its way through. Now instead of sitting here and drawing these all up, I have to show you one that I have already made, and you can see here that I've switched to a purple color, but the process is still the same. Now remember that each of the lines represents a crest, and each of the spaces represents a trough for the wave. Now depending on the distance that these two slits are apart, so what I'm going to do here is actually move one of them, is that we saw that they began to overlap pretty quickly. They were close enough to one another that they started to overlap fairly quickly. And so we get something that looks like this. And you can see that there's a distinct pattern that is formed in this image. If you look at this with water waves, that you can actually see this occur with water waves. So if I took two sources of a water wave and started oscillating them, so that could be like, my hands hitting on the water at a certain frequency, I could produce these two waves. Now, what's very important here, and the reason that this has to be monochromatic light in order to see the effect that we're trying to show here, is that both wavelets, so the source here and the source here, must have the same wavelength. And we'll see why that is in a second. Now, I want you to imagine if they didn't have the same wavelength. So that would represent in the picture that the concentric half circles that we see here would be closer together on one side than on the other. And we might not have this mapping out. Now, what we're going to do here is take a look at what overlap is actually happening. Well, I can see very distinctly that I can trace lines where I see overlap occurring. So I see the overlap of this outer crest over here overlapping with this crest over here. So I have two crests overlapping at that location. Same thing here, same thing here. And I also have locations where there are troughs overlapping with one another. So if I trace out these approximate lines here, I can see that I'll start to get some sort of pattern that's discernible and repetitious. And so I can see where there might be some sort of pattern where if I'm tracing these rays almost, that I start to see this very interesting pattern where I see those distinct pieces that might form the interference patterns that we saw over here. So you may not be convinced as of yet that that's exactly what is happening, but hopefully you're starting to see that there's some sort of interaction between the two wavelet sources here that we are seeing occur, and this might be what's causing it to happen. So we're going to look at this idea of interference, and this is seen in many different phenomena with waves. Sound waves, and water waves, all kinds of waves. And that is this idea of constructive and destructive interference. And this image is taken from the OpenStacksBC.ca website, where they have open source textbooks that are great, and I have a link in the description below. So if we see here that two waves are what we refer to as completely in phase with one another, we see that the crests of each of those line up with one another and the troughs line up with one another. And what ends up happening is that the two crests that are lined up create an amplified wave. It's the algebraic sum of both those amplitudes. So we could say the amplitude 1 and the amplitude 2 form this amplitude over here, and it is the sum of both of those amplitudes together. And the same thing happens with the troughs. And so what we see is that the maxima of the waves, those are the high points or the crests, and the minima of the waves reinforce one another. Now we have to be careful here. We're not saying one maximum and one minimum reinforce each other. We're saying two maxima reinforce one another and two minima reinforce one another. And so what that would correspond to is that we have brighter spaces than either individual of the incoming waves. So you can think of this maybe as wavelet 1, or a tiny little piece of wavelet 1, and this one as a tiny little piece of wavelet 2. And what we're seeing happen is that wherever they overlap in phase with one another, that they will create a larger amplitude, and so to make a brighter spot. Now, conversely, destructive interference would be where the maximum of the wave, or a crest of one of the wave, meets exactly in line with the trough of another wave. Now, if this happens exactly out of phase with one another, they're 100% out of phase with one another, what they will do is cancel one another out. This destructive interference is responsible for the dark bands on the wall, or the dark spots on the wall. And constructive interference is responsible for the light bands on the wall. And so what we can see then is, if we switch back to this view, is that wherever crests overlapped with the crests of the other wave, we would create light spots. And anywhere where troughs interacted, which is harder to see on these images, so we're going to look at that in the next video, that's where dark spots were formed. And so you can see here, this would be the location of the central maximum, and then on either side we would have a dark spot, then another light spot, a dark spot, and light, and so on. So in the next video, what we're going to do is take a look at how this particular experiment was done in terms of some of the geometry of the situation, and additionally the wavelength of the light.